Um, yeah, people hope so. I think we need the moisture, right? We absolutely do need the moisture. It'll be awesome. What do you think if I go backwards through the practice exam? Anybody? Should I go backward? Then we start with trusses. Should we start with trusses or should we start with our oldest thing? Should we start with equivalent systems? Anybody? Just I don't think it really matters. Why don't we go? If I can get OneNote to work here. Got a lot of slides on here or something. I think so, Basil. If you have an exam on Monday, we should. Sean says we should start in the middle with the 3D stuff. Okay, yeah, that sounds good. We can do that. Let's start right here. Okay, so this is problem number 16, and we have an FBD. Remember, in the review, I'm really going to think about this at a high level and like the process, which is, I think, the biggest challenge. It's not once you figure out the process and like the right FBD to draw and stuff like that, then yeah, there can be some challenges in solving the rest of that, but the process is really the thing I think we really need to focus on. Okay, so we are asked to draw an FBD of the pipe assembly that's supported by its cable at A here. So we have that cable right there. C is a journal bearing. Okay, so C we know is a journal bearing. And so journal bearing, we should know what that means. And then D is a thrust bearing. So at C, a journal bearing means it can have a force in two directions. And in this case, it would be in the Y direction and in the Z direction. And then at D, it's a thrust bearing. And so that tells us it can have a force in three directions, that we can have dy and dz. And then the thrust is what tells us there's that extra force that's along the shaft. So along the length of the shaft, and that shaft is really made to rotate. And then if our FBD, we really only have one choice for our FBD, and that's an FBD of the whole rigid object. There's only one rigid object here. It's of A, B, C, D, E to F. That's our only rigid object there, and so that's what we would draw over here. I'm going to draw it on top of our system here. The exam is all multiple choice, and so if we did anything with FBDs, it would be about picking the correct FBD on this exam. It is possible we will do some uploads during the exam, like draw the FBD and stuff like that this semester, but it doesn't look like that's going to happen on this exam on Tuesday. Okay, but it's still good practice on the practice exam to draw these, because even if we don't require it, you got to draw the FBD in order to solve these problems. Okay, so dx, dy, and dz, we got a cy and a cz. Now, these could have, both of these could have also a moment around the y and a moment around the z, at c and at d. But if we think about our FBD, the whole thing actually has, because we have a tension in AH over here, which we will express as a vector, which the vector will be the magnitude times the unit vector from A to H. So actually right now in that FBD, we have 6 unknowns. If we added the moments in there, we would have 4 more. We would have 10 unknowns. And so we don't need those moments, and it would be wrong to draw those moments on there. So there's our completed FBD. It's got the 3 forces at D, the 2 forces at C, and the tension in A to H, which we will express as a vector times a magnitude. Okay, now if we look at the next problem, they're asking us to find the force in A to H needed for equilibrium. So let's go back up to our FBD here. And do we have any pictures or any pictures? Yeah, we have pictures. We have a picture. Do we have any questions about this free body diagram before we figure out how we're going to solve for this magnitude in A to H here? Any questions about that? About the moments or anything like that? Okay. So how do we find TA to H? Well, remember last time we set up, when we did a 3D problem, we set up a roadmap. And we said in that roadmap, well, we know we have 6 equations. We have sum of forces in the x, we have sum of forces in the y, we have sum of forces in the z, and then we have sum of moments about a point. And I just said A. I don't know why I said A. There's not really, A would not be a good point to pick there, but we have sum of moments in the x, y, and z also. And so we have to pick for moments. We're going to look at x, y, and z, but we have to pick a point. And so we could pick either C or D would be really good for this problem, because at point D, we would get rid of 3 unknowns. At point C, we would actually also get rid of 3 unknowns, because the line of action for dx goes through point C. So C or D, both of those are I'm going to pick D. And so we have D in the x-axis. And we would do this, our moments about D in the y-axis. And we would do some of the moments about D in the z-axis. And maybe you wouldn't write all this stuff down during the exam, but you could certainly think about these. For example, if we're trying to find AH, what we're doing with this roadmap is just thinking about how many unknowns are going to show up in that equation. And does our unknown that we're looking for show up? Like sum of forces in the x, dx shows up. That's an unknown in that equation. But we're not looking for dx. We could solve for dx, but we're not looking for it. Sum of forces in the y. Well, that would include cy, dy, and this unknown tension from A to H. And I know that unknown A to H would show up because it's got a y component, and we're summing forces in the y. It's got, if we look at this, we can see from the picture, it's got a y and a z component, but it does not have an x component. Okay, so sum of forces in the z. Well, that would have a CZ, a DZ, and again, the tension from A to H. So I'm looking at this and I'm thinking, well, none of those equations are really going to help me. Now, what if I did moment about D in the x-axis? Well, if I did that, actually, that gets rid of everything at D, because those don't cause a moment about point D. And then it also gets rid of C, Y, and CZ, because those go through the x-axis right here. And since the lines of action go through that x-axis, then those do not cause a moment. So my only unknown is the tension from A to H. Well, now I know, okay, all I need is that one equation right there. I need moment about D in the x-axis. Well, how do I find the moment about D? I do it with the cross product. So we're going to take R from D to A crossed with that T from A to H. And then what else is causing a moment about D and the x-axis? Isn't it the 400 newtons? So it'd be also plus the R from D to F crossed with a minus 400 J hat. And I'm just looking at the picture here. The 400 is going down and it's in the y direction, so it's a minus 400 J. Now we just need to execute the cross product, and then we can, out of that cross product, we'll get IJK. We grab the I stuff out of that, and we can solve for the tension from A to H, which you will find all the details of that on the practice exam solutions, which were already up on Canvas. But there's our big picture, right? There's our steps. And we can apply these same steps to any three-dimensional problem. We say, okay, what equation do we need? And then, okay, if it's a moment equation, we're going to use the cross product. If it's a force equation, we just go into summing forces in the x, y, and z using our vector, knowing the line of action of our unknown vector there. Any questions about that? Okay, so we did 16 and 17. Let's move on to number 18 here, which is our trusses. And remember, we started in the middle of the exam. We'll go to the bottom and then we'll go back up to the top here. So which members are zero force members in the truss shown below? Okay, zero force members. This is our search and destroy. And we're only in that search and destroy. We're only searching for two things. We're looking for only two members meet. And the other thing we're looking for is that 3 meet and 2 are collinear. 2 of those 3 are collinear. And so we don't have to look at anything else. Now we do have to destroy stuff because that could open up a new joint in our search and destroy. So let's go. And then once we identify that, like H, there's only 2 that meet right there. We draw the FBD at H. We would have an HD, an HI right there. And we would also have this HY that's going straight up because that's a roller. So I know there's going to be a reaction there. I don't know what it is, but I know it's not going to be 0, right? That there's going to be some reaction there at HY that is not equal to 0. And so now if I look at this, if I sum forces in the Y direction, well, I'm going to find that HD is not equal to 0. Remember, I'm looking for specifically equal to 0. And then if I sum forces in the X equal to 0, I'm going to find that HI is not equal to 0 either. And so, so I'm going to say, okay, well, none of those are 0. I'm going to, over here at L, that's also 2 meet. I look at that. And so I'm going to find the same thing that I did over there at H, where I'm not going to get any 0 force members. So then I can go on to 3 meet and 2 are collinear. And so 3 meet, that would be at D. Well, at D, there's 3 that meet right there. And so I would look at that and I'd say, okay, well, let me draw my FBD at D. I'm going to have a DA, we'll have a DH, and then we'll have a DI. And so if I incline my axes, I'm going to incline my axes because I've got everything on the incline. If I sum forces in the Y direction, I'm going to find that DI is equal to 0. I'm getting explicit equation that's telling me that DI is equal to 0. So I'm going to destroy this. I'm going to, same thing at E. I've got 3 meet. It meets my search criteria. For the same idea that we did at D here, we would also find that DI is 0. Now that opens up I right there. And so at I, we will also find that that is equal to 0 based on the same FBD idea here, where we're going to sum forces in one of the directions and it's explicitly going to tell us it's equal to 0. And then B, that also meets our search criteria. So then this one goes away because of equilibrium at that point. At F, that meets our search criteria. This one then goes away. At G, that meets our search criteria. So this one goes away. Point K also meets our search criteria. But because we have this P going down there, we are going to find that this KC is not equal to 0 because there's an applied load there. So it did meet our search criteria, but when we draw the FBD, we're going to find that that one does not equal 0. So that's all of them. And I don't think, are there any other joints that now meet our search criteria? So based on these ones that I crossed out here, I think that's all of them, right? Like J doesn't meet our search criteria because there's 1, 2, 3, 4 right there. So we don't even have to look at it. If it doesn't meet our search criteria, we don't have to look at it. A right here, there's 1, 2, 3. There are 3 that meet, but 2 of them are not collinear, so we don't look at it. Over here at C, 1, 2, 3, 4. There's 4, so we don't even need to look at that. Any questions about that? Okay, moving on to number 19 here. What is the force in member AB? Our general process for trusses is FBD of a whole, of the whole thing, and that's to find support reactions. And then we need to pick an FBD of either a joint or a section to solve for our unknowns that we're looking for. Now, we may not always need to do the FBD of the whole thing. Well, let's take a look at this one. If they want us to find AB, well, that means I'm going to cut through that one right there. And if I cut through that one, how can I get an FBD that has that and doesn't have too many unknowns? Well, this is right at the end of that truss. So if I did an FBD at A, I would have A to B as unknown. I would have A to F as unknown. And I would have a known value of 4.8 kips. So, and a kip is 1,000 pounds. So actually, if I do and remember a joint, if we're doing a joint, we can only have 2 unknowns. And the reason is because everything is concurrent. We only have sum of forces in the X and sum of forces in the Y. We do not have sum of moments. But this works. And we can solve for AB by first doing sum of forces in the Y and solving for AF. And then we'll do sum of forces in the X and solve for AB. So that one, we didn't even have to do the FBD of the whole because we found an FBD that we didn't need to know what's going on here at F and what's going on here at G. Now, if we move on though to the next problem here, and we are now asked to draw a single FBD that allow you to solve for the force in GJ, GI, and HI. So GJ is here, GI is here, and HI is here. Now this should really say assuming the support reactions are known, because with this one, if we make a cut through here, and notice that I'm cutting through the middle of those truss members. I'm not trying to do this and cut through a joint. We can't cut through a joint. We need to cut through the actual yardstick, like when we did our yardstick truss. We need to cut through the actual middle of those members right there. And we can go either way. We can go to the right. That'll be totally fine. We could go to the left. But either one of those, we're going to need to know what BY is, and we're going to need to know what KY and potentially KX are equal to. If we go to the right, we go to the left, we need to know what BY is equal to. And I think on the next problem, actually they do tell us BY, right? So we, in this case, assume that we know the BY and KX and KY. Well, I would probably go to the right here then. It looks like I've got a little bit less stuff going on to the right, but the left would also work. Let me draw the pieces that were not cut. So none of those were cut right there. Now we did cut through that one right there. And we did cut through that one. And we also cut through that one right there. We would have an known KY, unknown KX. We would have our GJ right there. We would have GI right there. And we would have HI right there. With method of sections, and this is an FBD of a section, so this falls under method of sections, we can handle 3 unknowns because we can use sum of forces in the X, sum of forces in the Y, and we can use the sum of the moments about a point equation as well. So we have 3 equations that we can use for there. And so that means we can handle 3 unknowns. So we would need to add, to complete this, we need to add dimensions here for this to get full credit. And then once we add those dimensions, then we would be, that's a complete FBD there. And like I said before, if we went to the left of the cut there, that could also get you full credit, would get you exactly the same answers. A couple other things to note is, remember, we're drawing everything that's unknown are drawn in tension. So unknowns are always going to be drawn in tension. That way, if we get a positive number, we know it's tensile. If we get a negative number, we know it's compressive. Okay, and then For this truss here, same truss as before, but they're actually asking us now to find DG. I didn't like this when we gave this exam. I didn't like that we asked you for an FBD for one thing, and then we asked you to draw another. You have to draw another FBD to solve this one, because if we're going to cut through and find DG, well, we need to cut over here. Last time we were over here in between G and J. So you have to draw another FBD here. Which is fine. And so we were going to cut through DG, and actually we can go this way and cut through those two, or we can go this way. The thing we cannot do is cut through F, right? We never cut through a joint. Remember, we're always cutting through the center there. And I see a question here. So on our exam, we'll be finding a reaction of one of the members in the previous question. Yeah, I would like that would be better if we said, okay, now find GJ, right, instead of DG or something like that. And actually, let's assume that we did that. You could take a look at the solution of the practice exam. It's on the practice exam. This is good because you're getting more practice drawing FBDs, and so that's really good. But for the sake of time here, let's say we were asked to find GJ for this one right here. How could we find GJ? Well, think about your equations as options. If we sum forces in the X, how many unknowns are we going to have? Well, that's going to have all three unknowns. If we sum forces in the Y, that's going to have two unknowns. And actually, GJ doesn't show up. And we're trying to find GJ. So then we say, okay, well, what about sum of moments? And sum of moments is usually our most powerful equation because we can get rid of unknowns from that. So in this case, how can we get rid of GI and HI? Because we just want to be left with GJ. Well, look at where they intersect. Excuse me. They intersect right there at point I. And so if we summed moments at I equal to 0, we could find GJ. We would have to take into account KY, we would have to take into account KX, and then GJ would show up as our only unknown in that equation. Okay, similar thing on this one here. If we're looking for DG, I can go, let's say we went this way. Let's say we did an FBD this way, and actually that would be preferred because they give us BY. They don't give us the stuff over here at K. BY is 26.4 kilonewtons. So I'm going to include that known by going to the left there. Well, we'd have an unknown here, and unknown here. In this one, I could find DG by summing moments at F equal to 0. And then that would allow us to solve for DG. Okay, let's head back up here and let's think about, let's start with our equivalent systems. So our equivalent systems, the idea with equivalency is that we have two rules. And our two rules for equivalency is that we can't change the forces. We can move them and we can add them together, but we can't change the forces applied to the system. And the other rule that we had, so that's number one. Number two is that the moment about any point in the original has to be equal to the moment about any point in the equivalent. So then we can apply that to any problem that we're asked to find an equivalent force. For example, in this one, and this is asking us, we can identify these equivalence problems by just saying, okay, yeah, where is, or looking for those words like equivalent or equivalency and things like that. So this one, it asks us to replace the two force system with a force and specify its location measured horizontally from A. If you go back and look at the learning objectives, one of our learning objectives was to be able to draw the original and the equivalent system. So there's our original system. Let's draw the equivalent system. The equivalent system is going to be based on the problem statement. So they're asking us to replace it with a force and specify where it's measured from A. Now we know a force that is going to be equivalent between the 10 kilonewtons and a 15 kilonewtons is going to fall somewhere in between, and it's going to be based off of the weighted average. So it should be closer to the larger force there. So I'm going to draw it a little bit closer to that one. Our FR, because we can't change the forces that are applied to the system, it's just equal to 10 plus 15. And then where it's located, measured from A, is the X bar that they've shown over here in our possible answers. We can find that with our second rule. Our second rule says that we can't, the moment about any point has to be the same in both systems. Now, we got to figure out where we want to take the moment at. Well, we take the moment at wherever we're trying to measure the force from. They tell us measure it from A. So that means we're going to use point A in both situations, and we can find the moment about A in the original, and it's only the applied forces. So this is going to be relative to our positive sign convention. That's going to be a minus 10 times 1.5 and a minus 15 times 4.5. So that's the moment about A in the original system, but only the applied loads. We don't have to worry about the reaction at BY. And the reason that we don't is because the whole idea of equivalency is that what the BY and the AYs are going to be the same between both the original and the equivalent system. So we don't worry about supports at all. We don't worry about support reactions. When we're doing equivalency, we know that they're going to be the same, and we just entirely focus on applied forces and or moments. So we've got our moment about A of the original. We can find the moment about A of the equivalent is going to be a minus FR times X bar. And then we just have to set those two equal to each other. And we can set equal, and we will solve for X bar, and we get the correct answer there. Okay, gonna move along here. For the beam in problem 1, now they ask us a little bit different type to replace the original loading. Again, we see that equivalent term there with an equivalent force and moment at A. So our equivalent system now is going to look like this. They tell us where to put the force. And these were the two types of problems that we could see for equivalency. They either ask us where the force is located, or they tell us where to put it. And if they tell us where to put it, then we have to apply a moment as well. So we're always going to see an equivalent force and moment when they tell us where to put it. So we have our FR is here, and FR is the same. It's still going to be just 10 plus 15. We still have the exact same two rules. Now, in our original system, remember, we had found in the previous problem, we had found that the moment about A of the original was a minus 10 times 1.5 and a minus 15 times 1 times 4.5. And so we know we have a moment that's going, those applied forces are this moment that's going clockwise, because it's a negative, right? We get a negative, and we know that positive is going counterclockwise. Well, we lost that tendency to rotate when we moved FR all the way over to here, right? We had these two forces out here, and they were causing, I got to turn off my virtual background here. Choose virtual background, and how about none? Okay, there we go. Right, so they were causing a rotation like this. Well, if we move the force over to here, there's nothing causing a rotation on that system anymore. And that's where the second rule comes in, is that we have to have a moment about point A. Well, what does that moment about point A have to equal? Well, we still have our second rule. The moment about A of the equivalent system has to be equal to this stuff up here. Well, the only thing that's causing a moment about point A in our equivalent system is that moment about A. And it's going, the way I drew it, it's going negative. So we'd say, well, negative MA has to be equal to minus 10 times 1.5 minus 15 times 4.5. So we can, so then we can solve for that MA in that equivalent system. Okay. Now, what about when a problem gets a little bit more complicated, where now we're still asked for an equivalent resultant force and specifies location measured from point O? The process stays effectively the same. The only thing that's different here is that we now have forces with X and Y components. So when we have forces with X and Y components, let's just figure out what is our FRX and what is FRY. Because remember, we can't change the applied forces, but we can add them together. So FRX would be 300 times the cosine of 30 for this one. It would be plus 200. It would be minus 150 times 4/5. And so we figure out, okay, well, FRX, we figure out an exact number there. FRY is going to be 300 times sine 30 plus 3/5 of 150. And so now we have FRX and we have our FRY. Now we can draw our equivalent system. Our equivalent system is going to look like this. And I think, let's see, we're going to have FRX is going to go to the right, I'm pretty sure. And FRY is going to go up. So I'm going to draw, and they're asking us to measure, where is that location measured from point O along the line from O to C. So they're telling us where to put that, the resultant force, right? O to C is that line there. So somewhere along here is going to be our FRX and the FRY. Now, it may seem really simple that we're drawing this equivalent system, but this is really going to help us when we go to figure out, well, what is that distance right there? That's what we're looking for. Let's call it Y. They want us to find that distance. Well, we already found the X and Y components of FR, but now we need to figure out, okay, well, what is Y? We do it the same way we did before, where we're going to take the moment about O, because they're asking us to measure things from point O, and we're going to figure out what are all these forces and this moment up here. What moment are we going to have about point O in our original system? Well, it's going to be relative to our positive sign convention. It's going to be 40 foot-pounds. That's just a couple moments. So it either adds or subtracts depending on what direction it's going. And then we'll have the 150. That will have the horizontal component will cause a moment about point O. The 200 will cause a moment about point O. The horizontal component of the 300 will cause a moment about point O. So we're going to get all this stuff about the moment about point O for the original, and then we can use our picture of our equivalent system to find the moment about point O of our equivalent. And so this will be a minus FRX times Y. And so it makes that coming up with that equation just so nice and easy. When we draw that picture, we can see that FRY does not cause a moment about point O, because the line of action of FRY goes right through that point there. So lots of advantages for drawing that picture of that equivalent system. Also, we can see that the process is effectively the same. Only difference here is that we had an FRX and an FRY. We had to pick a different point to take the moment about. We had to incorporate the couple moment, but otherwise, like, our overall process is the same. Okay. Oh, and I see a question here. Why don't we consider BY? Okay, so this was on this one back here. We don't consider BY in either one of these. We don't consider BY in this one or in this one. We could, if we really wanted to, we could say, well, there's a BY here, but then we also have to take into account this BY down here. And we know for equivalency that those are the same. That's what it means to be equivalent, is that these are the same between both the original and the equivalent system. So if we did incorporate both of them, there would be a plus BY times 6 in here, and there'd be a plus BY times 6 down here. And when we set them equal to each other, they would cancel out. So that's why we don't have to consider those support reactions. We don't have to solve for the support reactions. We just have to use the applied forces and our moments. Like this one down here, it doesn't matter what the reaction moment is at O, right? We don't have to worry about that. That's a fixed support, but we don't have to worry about any of those reactions at that fixed support. We're entirely focused on the applied forces and moments. Good question. Thank you, Basil. Okay. What is Y tilde for representative? I'm going to go ahead. I feel like, that's more of mathematical type stuff. I'm going to skip through some of these. Actually, maybe if we get some time at the end here, we can come back to those. Let me move ahead out of those centroids, and let me go to our to this one, which is asking us to find the magnitude of the resultant force for the distributed load shown below. The distance from A to B is 12 feet. So we know this is a 12-foot distance right here, and they want us to find the magnitude of that distributed load. What do we do with distributed loads to find the magnitude? We break it up into, for a trapezoid, a rectangle, and a triangle. It's just the area of the triangle and the area of the rectangle, and that's going to give us an FR1 at the centroid of the triangle and FR2 at the centroid of the rectangle. And so FR1 is just the area of that triangle, and FR2 is the area of the rectangle. So the distributed loading should be really quite straightforward. In this one, where is the location of the resultant force measured from point A? That's exactly the same problem as our first problem on equivalent systems. We have the centroid for the triangle is about here. The centroid for the rectangle is there. So we have those two forces. We are just looking for the weighted average of those two, which is the same as question 1 on this exam in order to solve that problem. Okay, let's move into some 2D rigid body equilibrium here, though. So our 2D rigid body equilibrium, the reason that we know that is, how can we figure out, oh, this is rigid body equilibrium? Well, we could do process of deduction, right? It's not 3D, it's not a truss, and it's not asking us for some equivalent system. So by the process of elimination, we know, okay, well, this must be 2D rigid body equilibrium. So they're asking us that if this tractor is lifting 900 pounds, what is the minimum weight that needs to be applied at G so the tractor does not tip? So when we're in rigid body, anytime we're doing equilibrium, anytime we're asking for a force, an unknown force, we're going to have to use our equilibrium equations. Well, to use equilibrium equations, we need FBDs, don't we? Now, the FBD that we're going to use for this is the whole tractor, and that's because the whole tractor is what's going to tip. That means we would have a normal force here at A, a normal force here at B, this weight there, which is what we're trying to find, and then we have our 900 pounds that's applied right there. Now, right now, I've got NA, NB, and W. However, I can't solve it yet. I need to figure out the value for NA. If we do tip, what's going to happen? This wheel over here is going to come off the ground, isn't it? And when we're right on the verge of tipping, NA is equal to 0. This is going to be our pivot point right there. If we do end up tipping this tractor over, we know then that NA is going to be 0, and we can solve for this W by summing moments at that pivot point B, setting it equal to 0. Our only unknown in that equation is going to be this W. In fact, it's going to be a W times 40 inches, and then a minus 900 times 50 equal to 0, and we can solve for W. So got to think about our FBD first. Anytime we're doing equilibrium stuff, we got to draw those FBDs. In this one, we're asked to draw an FBD of ABC, which is supported at C by a fixed support. It says provide enough information on the FBD to solve the problem, right? We should be able to solve the whole thing without going back to the original problem statement. So fixed support at point C, well, what are we going to have there? We know, if we think back to how we figured out what forces and moments go at these different supports, we asked ourselves, what does this allow happen and what does this prevent from happening? Well, this prevents translation in the X, it prevents translation in the Y, and it prevents rotation as well. So a fixed support is going to have an MC, a CX, and a CY. It doesn't matter what direction I draw those in. And then I would need to finish labeling this with the 500 pounds per foot. And this would be 15 over 2 and 15 over 2. And that would be my completed FBD. Now it's asking us to determine the reactions at that fixed support C there. I'm going to go ahead and I'll probably go until about 155 or so and just at least get through this rigid body stuff. If you've got to run, I understand. So how are we going to solve, right? It's asking us to find the reactions at C. Given the same W, same L as our original FBD up here. Well, we've got 3 equations and 3 unknowns. So if we sum forces in the X, we're going to have just a CX, and we'll find that's equal to 0. If we sum forces in the Y, we're going to have a CY that's going up. We also have our 500 pounds per foot that's acting over 7.5 feet. And so we will need to figure out our resultant of that distributed load and also know where that acts. Well, that's going to be at a distance of 7.5 over 2. From there to there, but then we're going to also need the whole distance all the way from that FR all the way back to this wall right there. So we'd have a CY, and then we'd also have a minus FR equal to 0. And we know that FR is equal to the area under that distributed load, so 500 times 7.5 would give us our FR. And then we can find the moment at C by summing moments at point C. And if we sum moments at point C, CX and CY go away. We do have an MC, and I drew it going counterclockwise, so it's positive. Now this is 2 different things, right? I'm writing the equation, summing moments about C, and I also have a moment reaction at C. Those do not mean the same thing, right? Summing moments, that's everything that causes a moment about C. MC is the reaction moment at point C. So we'd have an MC, which is positive, and we'd have a positive FR times that distance there of 7.5 over 2 plus another 7.5. That would be equal to 0. We could solve for MC. By the exam, that should be a pretty straightforward problem. This problem, another 2D rigid body equilibrium problem, similar to one of our homework problems in that we had 2 rigid objects. In this one, we have B, C, and D are pins. What are the magnitude of the reactions at B? The dimension A is 1.0 inches. So when we have more than one rigid object, we need to think about what type of objects are these. This one right here, A, B to D, that is a multi-force object because it has 1, 2, 3 locations where forces occur. C to D only has 2 locations with forces, so it's a 2-force member. When we have a 2-force member, the line of action always goes between the 2 locations where those forces occur. Our choices for FBDs is really just that multi-force member. So if we draw an FBD of that multi-force member, we need to be able to figure out, okay, I've got 50 pounds. And another thing that keys us in to the correct FBD is that we have a known value on ABD. We don't have any known values on C to D. At B, this is a pin support connected to a multi-force member. So this is going to be a BX and a BY. Now over here at D, that is a pin connection, which can be DX and DY, but this is a 2-force member, so we have a known line of action, and we need to write this as F from C to D. We need to incorporate the geometry of that right there, figure out what that angle is. Now we have an FBD with 3 unknowns. If you did not identify C to D as 2-force, you would have a DX and a DY. That would be too many unknowns. You wouldn't be able to solve the problem because we only have 3 equations. So now if we want to find BX and BY, we have 3 unknowns. So it's just a matter of looking at our equations as options. If we sum forces in the X or Y, or if we sum moments. Well, I always like to start by looking at the moment equation. If I sum moments at point B, that's going to get rid of 2 unknowns. It's going to get rid of BX and BY. So that's a really good place to sum moments at. Now that's going to allow me to find FCD. So now I just solved for FCD. It's not what I was looking for, but if I sum forces in the X to start with, I would have 2 unknowns. If I sum forces in the Y, I would have another 2 unknowns. So I couldn't start with forces in the X or the Y, but now I can go into forces in the X and I can find BX, and I can go into forces in the Y and I can solve for BY. Let me do one more here, and that's relevant to the 2-force and multi-force members. This is asking us to circle all the elements that are 2-force members in this frame. And I see a comment in the chat there. It looks like this test might take more time than the last one. I think the last one was a little bit long. I hope, we had a lot of cross products on the last one, so that did take a while. I'm hoping this one isn't quite as long, but still challenging. Okay, so circle the ones that are 2-force members. Well, 2-force members just means that there's only 2 locations. This one right here, this has 3 locations. 1, 2, 3. B to C. This one has the distributed load over the whole thing, and B and C, so that has 3. A to C, this one here is only 2 locations, A and C, so that's a 2-force member. And then C to D, also only 2 locations, so that is also a 2-force member. Yeah, and the last one took the whole time as well, Kieran, absolutely, you're right. Okay, I'm gonna go ahead and stop there. If you have any questions at